Hello students and friends. In this video, I'll be discussing two problems on thermal conduction and radiation. So just hang on, watch, and learn. So what is thermal energy conduction? It is a mode of energy transfer via collisions of atoms or molecules. Consider metal rod with end A being heated over a plane. So we have here the rod. This is end A and that is end B. Let's say that the temperature at end A is at a higher temperature and we label it as T sub A, while the other end B, has a temperature that is much lower than T sub A, and we label it as T sub B. We also have the length of the rod represented by letter L. And of course, we have the cross-sectional area of the rod. The time it takes for thermal energy to be conducted from point A to point B, we will call it time elapsed T. And capital Q would represent the amount of thermal energy that is being conducted by this metal rod. And we say that the amount of energy, capital Q, depends on factors like the cross-sectional area, the temperature difference, that is T sub A minus T sub B, or the higher temperature minus the lower temperature, the time of conduction. All those factors that I mentioned, we say, will affect the amount of energy. The relationship with Q is that each of them is directly proportional to Q. The only variable or quantity that is inversely proportional to Q is the length of the rod. So all these factors, when related to the amount of energy Q, can be expressed in one simple equation. That is, the amount of energy that is being conducted, capital Q, is equal to the product of the cross-sectional area, capital A, the temperature difference, delta T, and the time of conduction, small letter t, divided by the length of the conducting material. Small k is what we call the constant of proportionality, which is specifically called the thermal conductivity constant. And its formula, all right, when this equation is transposed so that we will have the thermal conductivity, small k, on one side of the equation, it will result to this simple formula. K is equal to the product of Q times L divided by the product of the cross-sectional area, the temperature difference, delta T, and the time of conduction, T. What does the value of thermal conductivity represent? Well, we have here a list of common materials with their corresponding thermal conductivity. The unit for conductivity, thermal conductivity, is in watts per meter Kelvin. You will notice that among these materials, diamond has relatively the greatest value for conductivity. And among common metals, we have here silver, copper, gold, aluminum, tungsten. Okay? And their thermal conductivity is in an descending order. In other words, among these common metals, silver has the highest conductivity or thermal conductivity constant. You will also notice here that wood, which is a common material for a lot of houses, all right, its thermal conductivity is relatively very low, only 0.1 to 0.2 watts per meter Kelvin, as compared, for example, to a hollow block, that is made of concrete, another type of material commonly used in building construction. Its thermal conductivity is a little bit higher compared to that of wood, which is 2.25 watts per meter Kelvin. And you will notice here that air is a very poor conductor of thermal energy. It has only 0.026 watts per meter Kelvin as its thermal conductivity constant. For our first example, we have here problem number 1, which reads, one end of an insulated metal rod is maintained at 100 degrees Celsius, and the other end is maintained at 0 degree Celsius by an ice-water mixture. The rod is 60.0 centimeters long and has a cross-sectional area of 1.25 square centimeters. The thermal energy conducted by the rod melts 8.50 grams of ice in 10.0 minutes. Question is, find the thermal conductivity K of the metal. So, as usual, we will identify each of the given quantities in this problem. Okay, so we have the temperature of one end of the metal rod, which is labeled here as capital T sub 1, and it is equal to 100 degrees Celsius. All right. The other end of the rod has a temperature capital T sub 2 equal to 0 degrees Celsius. Okay, this temperature is, as the problem mentions, this is maintained by an ice-water mixture. We also have the length of the metal rod, capital L, which is equal to 60.0 centimeters. And the cross-sectional area of the metal rod is given as capital A equals 1.25 square centimeters. All right. Now, the mass of the ice, all right, is equal to 8.50 grams. There is a constant known as the heat of fusion of ice, labeled capital L sub F. And this is equal to 33.5 raised to the fourth power joules per kilogram. This is the amount of energy that is needed for ice, or exactly 1 kilogram of ice to melt, right? This is the amount of energy that is needed in order to melt a 1 kilogram mass of ice. And we usually call it the latent heat of fusion for solid water such as ice. Now, again, according to the problem, it takes 10 minutes, or its equivalent in seconds, of course, is 600 seconds. It takes 600 seconds for this amount of ice, 8.50 grams of ice to melt, okay? Because the thermal energy is being conducted, okay, from the hotter end of the rod, all right, to the other end of the rod where there is an ice-water mixture. And since this amount of energy that's being transferred will be absorbed by the ice, causing the ice to melt. And according to the problem, the time elapsed, or the time during which, all right, the energy is being transferred by a conduction is exactly 10 minutes. Within this 10 minutes of time, this amount of ice, 8.50 grams, will melt. All right? So we are asked to find the thermal conductivity K of this metal. All right. So how are we going to answer this question? All right. As earlier presented, the formula that we need, first, we have to calculate for the amount of thermal energy that is required, all right, that is required to melt this amount of ice, all right, 8.50 grams of ice. Since you are given the constant latent heat of fusion, or LF, we can calculate for that amount of thermal energy, capital Q. Right? So we will be doing that a little later. Once we have determined the amount of thermal energy, capital Q, then we can use the second equation, all right, earlier presented also, where capital Q is equal to the product of K, capital A, delta T, multiplied to the time T all over the length L. All right? So all we need to do is substitute whatever is the amount of thermal energy that we calculate using this formula, Q is equal to mLF. We're going to use it here in the second equation, but our task is really to determine the value of the thermal conductivity K using the derived formula. So the first formula that we're going to use is Q is equal to the mass of the ice that melts multiplied by the constant heat of fusion. Substituting the values for the mass of ice that melts, already expressed in kilogram, and the heat of fusion, which is also expressed in the SI unit, we will get the amount of thermal energy that is conducted, all right, within this time of 10 minutes. And that is also the amount of energy that was required to melt, okay, this amount of ice. So Q is 2,850 joules. So our next step is now to calculate for the thermal conductivity constant, small k, using the formula capital Q multiplied by the length L divided by the product of the cross-sectional area times the difference in the temperature delta T and the time elapsed small t. So substituting the given values, this is what we get, right? Again, all the quantities are expressed in their SI units, right? So our computed value for Q is 2,850 joules. The length of the rod already expressed in meter is 0.600 meters divided by the cross-sectional area, again already expressed in square meter, 1.25 raised to the negative 4 meters squared. The temperature difference, delta capital T, is 100 Celsius degree, and the time expressed in second, which is 600 seconds. And what we get when you use your algebra is a value of K equals 228 watts per meter Kelvin. Question now is, this value of K is an experimental value, all right? If you're going to compare this value to what we have listed in our table, so take note, it is 228 watts per meter Kelvin. So we shall find out what particular metal is the rod made of. All right, so comparing the computed value for the thermal conductivity of the metal rod, it looks like that 228 watts per meter Kelvin is very much close to the thermal conductivity of this metal, aluminum. All right, so the standard value is 247. Our computed value was 228, so not very far. We therefore conclude that the metal rod used in that problem has relatively a high thermal conductivity constant. All right, so our second mode of thermal energy transfer is what we call thermal radiation. Okay, so when bodies uh, have their molecules in translational motion and they emit energy in the infrared range with intensity that's related to the Kelvin temperature. All right, so infrared, as you all know, is one member of the electromagnetic wave spectrum. That's why this kind of thermal energy transfer is quite different, all right, from what we have earlier. It's different from conduction. It's different from convection either, because thermal radiation is an example of electromagnetic wave. The process is electromagnetic wave propagation, which again, I'm sure you all know that uh, EM waves do not require a material medium for them to be able to be transmitted. All right. So the energy that we get from the sun, all right, is transmitted to the earth in the form of what we call radiant energy or solar energy. So anything that's, shall we say, of higher temperature compared to its surrounding, okay, has the tendency also to emit infrared radiation. For example, in this diagram, okay, we are able to feel the warmth coming from this burning logs, okay, because the energy that is being emitted, the infrared radiation that's being emitted by this body is transmitted, all right, to our hands via what we call electromagnetic wave, in particular through infrared radiation. All right, so we use the Stefan-Boltzmann law of radiation in order for us to quantify the amount of thermal energy that's being radiated. All right, so the Stefan-Boltzmann law of radiation uh, simply describes that the radiant energy, capital Q, emitted in a time, small t, by an object that has a Kelvin temperature, capital T, and a surface area, capital A, and an emissivity labeled small letter e, right? Emissivity gives you the ability of a source to emit radiation, right? The best emitter is known as the black body radiator, and the value of emissivity for these bodies is exactly equal to 1.0. Emissivity is a unitless value, all right? So for common materials, other than black bodies, the emissivity value that they have are usually less than 1. The formula for Stefan-Boltzmann law of radiation is simply capital Q is equal to emissivity, small letter e, multiplied by the Boltzmann's constant, labeled here by the Greek letter sigma, multiplied by the Kelvin temperature expressed to the fourth power, multiplied by the surface area, capital A, and the time of, or the elapsed time, all right, the elapsed time for energy to be radiated from one point or one region to another. That is what is meant by small letter t, which is incidentally, when small letter t is isolated or transferred to the other side of the equation, it will become the denominator of big Q. And big Q divided by small t will, of course, be referred to as the rate of thermal radiation, meaning how fast the thermal energy is being transmitted, all right, from one point to another, or from one body to another. All right. So, as mentioned earlier, sigma represents the Stefan-Boltzmann constant. Its value, all right, is equal to, sigma is equal to 5.67 raised to the negative 8 joules per second meter squared Kelvin to the fourth. All right. So we're going to look at sample problem on thermal radiation in a short while. Also mentioned earlier, the emissivity of a black body is exactly equal to 1.0. For other bodies that are not considered black bodies, their emissivity values are usually less than 1. A very perfect or a perfect reflector, right, has an emissivity equal to 0. In other words, emissivity values for good radiators can range from or between 0 to 1. So our sample problem number 2, the rate at which radiant energy from the sun reaches the Earth's upper atmosphere is about 1.50 kilowatt per meter squared. The distance from the Earth to the sun is 1.50 times 10 to the 11th power meter, and the radius of the sun is 6.96 times 10 to the 8th power meter. Question letter A, what is the rate of radiation of energy per unit area from the sun's surface? Letter B, if the sun radiates as an ideal black body, what is the temperature of its surface? Right. So as usual, we will identify the given quantities. All right. So the quantity mentioned 1.50 kilowatt per meter squared can also be referred to as the intensity. All right, the intensity of radiation, labeled here as I sub 2. All right, uh, the subscript I sub 2 meaning when the radiation reaches the Earth's upper atmosphere. All right, that is what we will consider as, uh, in other words, region number 2. All right. Remember, the source of radiation, of course, is the sun. So when this radiation is emitted by the sun, it reaches the Earth's upper atmosphere at this, what we call, intensity. All right. Take note, the unit for intensity is kilowatt per meter squared. So that is our I sub 2. The distance di, which is 6.96 times 10 to the 8th power meter, in this problem, it refers to the radius of the sun. All right? So, Why is this our distance number 1? Because we are assuming that um, the region, the region as being described by our question letter, what do you call this? Letter A, what is the rate of radiation of energy per unit from the sun's surface? All right. So, how far is the sun's surface from the center of the sun? Meaning from the core of the sun. That is, of course, equal to the radius of the sun, whose value is given 6.96 raised to the 8th power meter. And that is what we are going to refer to as our distance number 1. Right? Our distance number 2, all right? Distance number 2 is how far is the center of the sun to the upper atmosphere of the earth. All right? Now, since the radius of the earth is given, d1, all right? And the distance from the sun to the earth likewise is given, okay? If we add these two distances, all right? Then we are talking about how far is the upper atmosphere of the earth from the center of the sun. So that is what will be represented by d sub 2. The quantity that is being asked in letter A, rate of radiation of energy per unit area from the sun's surface, of course, will be labeled, all right? It will be labeled as I sub 1. And that is our unknown variable, I sub 1. Take note, we are also assuming that the sun is an ideal black body. Hence, its emissivity value is equal to 1.0. Okay, the sum of 6.96 raised to the 8th meter and 1.50 raised to the 11th power meter, when added, this is what we will get, 1.51 raised to the 11th power meter. All right, so that will be the value for our d sub 2. Now, how do we go about determining the answer to letter A? All right, we use the formula I sub 1 multiplied by d sub 1 squared is equal to I sub 2 multiplied by d sub 2 squared. Right? This formula is the mathematical version of the relationship between intensity and the distance. All right? Intensity of radiation, this formula is one of the several formulas in physics that obeys what we call the inverse square law. In other words, the intensity of radiation is inversely proportional to the square of the distance. In short, as we go farther from the source of the radiation, of course, the amount of intensity, okay, becomes smaller. But more specifically, okay, the change in the intensity is such that it is inversely proportional to the square of the distance. So if such a relationship is converted into a mathematical equation, this is what we will get. All right, I sub 1 multiplied by d sub 1 squared is equal to I sub 2 d sub 2 squared. Take note, we are looking for I sub 1. So that formula, of course, will be used. Okay, once we are able to calculate for intensity number 1, that is what we are going to use to determine the answer to letter B. all right? Finding the temperature of the sun's surface, all right? Again, using the Stefan-Boltzmann formula, all right, where Q, all right, was earlier determined as the product of emissivity, sigma, temperature, Kelvin temperature to the fourth, multiplied by the surface area and the time t, all right? And since intensity refers to the amount of energy that is being transferred per unit area, all right, per unit area, rate of radiation of energy per unit area, and that term q over q divided by the area times the time t is what is meant by rate of radiation of energy per unit area, which we label as capital I, all right, for intensity. So in letter B, what we are looking for is the temperature. So all we need to do once we get the value for I using the first equation, we substitute it here and determine the Kelvin temperature, capital T, with a working formula that is T is equal to 1 divided by emissivity multiplied by sigma, all right? All this term, all right, 1 intensity divided by emissivity sigma. Remember, take note there is a quantity or parenthesis. Okay, this will be what you call, this will be inside a radical with the fourth root. In other words, we will be getting the fourth root of this quantity, intensity over emissivity multiplied by sigma. So we will see our computations in a short while. All right, so our first computation is for intensity I sub 1. Okay, so substituting the given values, we will get 1.50 kilowatt per meter squared, that is I sub 2, multiplied by d sub 2, then square it, 1.51 raised to the 11th power meter, all right, square. Then divide this by the square of d sub 1, 6.96 raised to the 8th power meter. Doing your algebra, okay, what we get is I sub 1 equals 7.07 times or raised to the 7th power watt per meter squared. We are particular about the number of significant figures in this computation. No? So all the given, as you notice, are all expressed in 3 significant digits. That's why our answer is also expressed in 3 significant digits. All right, so this is the intensity I sub 1. The intensity of the radiation of the sun at its surface. All right, for letter B, okay, whereas to determine the temperature of the sun, of the sun's surface. So our formula is simply using this. T to the fourth is equal to intensity divided by emissivity multiplied by sigma. All right. We will be doing the fourth root or extracting the fourth root towards the end of our computation. All right. So we first substitute the value of the intensity that we earlier obtained here, 7.07 raised to the 7 watt per meter squared. divided by the emissivity of the sun, which is assumed to be equal to 1.0, the Boltzmann's constant, 5.67, raised to the negative 8 joules per second meter squared Kelvin to the fourth. Doing your algebra once again, right? We will get the value for the Kelvin temperature at the sun's surface, which is capital T equal to 5,960 Kelvin. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.